introduction, and it's really a great pleasure to give a talk here, especially where I can call hometown. So let me start with basic definitions. The graph homomorphism, probably you would all know, but graph homomorphism is a vertex map between two graphs that preserves adjacency. So whenever fu fv is an edge, whenever uv is an edge. And graph homomorphism density th of g is a probability that a random vertex map is a homomorphism. So the number of, so this is a set of all homomorphisms from H to G, and then I divide it by the only possible number of vertex maps. So this is a basic definition. And so I'm going to talk about a question by Koyakawa, Rodel, Nagel, and Schacht. And there are a few different motivations on the question. Before getting to the question itself, let me briefly motivate in a different ways. So the first motivation for the question is a quasi-randomness. So quasi-randomness, defined by Andrew Thomason and Chong, Graham, and Wilson in 80s, is a formalization of pseudo-randomness of graphs. So these pseudo-randomness versus some structured piece is a kind of very, has been a very successful philosophy to attack many modern problems in mathematics, and quasi-randomness, one of these cornerstones in graph theory, saying that, so a graph sequence Gn, let me start with a graph sequence Gn with number of vertices that tends to infinity, is quasi-random. There are several equivalent definitions, and I'm just going to talk about only a few of them. Firstly, the most natural one is for any fixed graph H. Let me put another condition that the edge density tends to some fixed p. If it's sparse, then it gets messier. So the normalized H count is random-like. So if you consider a random graph, then you would have such a concentration on the mean. So it basically says that for every fixed graph H, you have a random-like count for H. Secondly, so all these are equivalent. So all these are equivalent. And it is well known that it is enough to check this random-like count for some bipartite graph, in particular the full cycle. And another interesting condition is that given any vertex subset of G, so here all the G's are Gn's, sorry. So for any vertex subset of X, the edge count in X, so which means, this means the number of edges induced on the subset X, and this is again random-like plus little of Gn squared. This is again random-like. So here I have here the half factor comes from the, so the P is for labeled edges. And here I count the just number of edges, so that's why I have half of P here. So the third condition means that for every subset, if I have a random like count for edges, then it's actually equivalent to being quasi-randomness. So
G, do you assume that the vertex set is like fixed or something? X is a subset of VGN, but N is changing, right? And you take N going to the infinity, right?
Yes. So this should be phrased in terms of epsilon. So given any fixed epsilon, there exists large N, such that given any subset of X, blah blah blah. Okay. Yeah. So that's quasi-randomness. And a natural question here is, can you relax some of these conditions, and with these somewhat weaker condition, we can guarantee some sort of random like count for graphs. So this is very vague. So one question is, if some do some weaker conditions imply somewhat weaker pseudo-randomness. And this question, well, there would be many questions in this line, but one natural thing is, what if we guarantee the lower count for edges for large enough subsets is large enough, which means locally dense. So given any large subset of vertices, I can guarantee that there are many edges inside the subset. Then can you still guarantee that there are many copies of H? So this is one. So that makes 3 weaker, and actually some sort of something similar to condition 1 holds. So here's a formal question. This is by Koyakawa, Rodel, Nagel, and Schott. So for any H and for any given small real number eta, and given some fixed number d, so these are all arbitrary positive numbers, and there exists some rho which depends on eta, d, and h, and some n0, which is also depends on the 3 parameters, such that the H count in G is, so we just give a lower bound for H rather than the upper bound. 1 minus eta to the d to the number of edges in H whenever G is locally dense. So let me just write the question in locally dense and with at least n0 vertices. So this is a question. And still, I have to define what locally dense means. So a graph G is, so this definition, graph G is rho d dense. So here I have to change this into rho d. If whenever X is a large enough subset, whenever X is a large enough subset with rho proportion of the vertices, then I have the edges at least, edge density at least D on X. So this means given any given G, if I take a rho portion of vertices, and I can guarantee that there are at least the edge density is at least D for every such subset. So this means I just have the lower bound for the number of edges in every subset, not every, but large enough subset of X, large enough subset X. And then that lower bound also guarantees the existence of H in a random-like way for lower counts again. So this was a question. And this is not really an arbitrary variant of quasi-randomness, and it also has some applications in remedy theory. So let me... So here's another motivation on remedy theory. So when you consider Ramsey numbers of some graph, so here's my Kn. When you consider Ramsey numbers, we often just color Kn with two colors or R colors. Say, let's just stick to two colors. So suppose we colored the edges of Kn in two colors. And what we'd like to do is to find H with some bounded degree. Suppose so. Find monochromatic H with bounded degree. Then the usual strategy here is, so there are two colors, say red and any other? Okay, white and red. So if there are really many red edges, say over here, if I have a very, very dense red graph, then I'm quite happy, because so the first case is in some subset, some large subset, I have red density, say at least 1 minus 1 over 8 delta, or, well, to be safe, let's say 20 delta. Yeah. Then I'm happy, because such a graph would contain a large bounded degree graph. This is an easy case, if you believe me.
As a subgraph.
Yeah, as a subgraph. So if there's such a very dense red graph, then we're happy. So this is the first case, and often it's considered to be easy to handle. And the second case is the otherwise. What if we don't really have such a dense patch of red edges? Then that means for any X with large enough proportion, we have instead the white edges at least this much. So either red edges are very dense in some subset, or white edges are spread on everywhere. So this second case is again boils down to these rho d denseness, and hence finding some H copies in this second case efficiently, like this many, is an important question in remedy theory. And there's another motivation behind this question is conjecture of Sorrentos, which states that for any bipartite graph H and for any graph G, the number of H in G is essentially minimized by the random graph G and P. So can you spot the similarity over here? So here, the quasi-randomness is P to the number of edges in H. And here I just guarantee that's actually the minimum for bipartite graphs. So, and the statement here, the random lower count over here is somewhat reminiscent of the Sorrentos conjecture. And there's actually some application of some connections between these two conjectures. So I'm not going to talk about that much, but too much. But so the theorem by David Cullen and Jung-Han Kim, Joonkyung Lee, and myself states that if H satisfies the KNRS conjecture, say, so let's say this is the KNRS conjecture. Yeah. Even though actually Matthias didn't look quite happy to say that this is a really conjecture. Yeah, he rather just say it as a question. But anyway, so if H satisfies KNRS conjecture, then replacing each edge of H by a path of length 2 gives a bipartite graph. So let's say H bar or H dot, say H dot. So this is the one subdivision of H, satisfies Sorrentos conjecture. And there's also a philosophical reason behind this random lower count is somewhat similar. And if we could do well on here, and then we might expect that we could do something on here. So these are all the motivations behind this question. And then let me say so what's known so far? Oh, and I should have said that if a bipartite graph H satisfies Sorrentos conjecture, and then obviously it also satisfies Koyakawa-Nagel-Rodel-Nagel-Schwarz conjecture, because I can just take these eta to be 0 and I can just drop off these rho dense condition. So it trivially, if bipartite graph H satisfies Sorrentos conjecture, and then it also satisfies KNRS conjecture. So this is an obvious implication over here. So what's known so far is for bipartite graphs, the known instances are just those from known instances of Sorrentos conjecture. So I'd be very, very happy to see the difference between two conjectures. I mean, if there's only a single instance of bipartite graph that is not known to be Sorrentos, but to satisfy that conjecture, then I'd be very happy. But still, so far, every known instance of KNRS conjecture relies on Sorrentos conjecture for bipartite graphs. For non-bipartite case, So
So you mean every bipartite graph satisfies pseudo-Renko's conjecture?
no. So what I meant was so every bipartite instance of KNR's conjecture relies on the developments on Sorrentos conjecture. So I'd be very happy to see this difference between two on bipartite case. So if there's one single bipartite graph that is unknown to satisfy Sorrentos conjecture, but satisfy this conjecture, then it would be very interesting. And so for a non-bipartite case, what's known so far was complete multipartite graphs. This is folklore because it's Koyakawa, Nagel, Roder, and Schacht wrote that this conjecture holds for complete multipartite graphs, but they've never written it up. But yeah, well, but you can find it, the proof on my paper on arXiv. But it's folklore and not that much hard. And then Christian Reyer showed that odd cycles satisfy the conjecture. So this has been all the known examples before my work. And my result is we may glue these known instances which are complete, say L-partite, or odd cycles to obtain new instances. So I'm gonna explain what glue means I forgot to say that, in a tree-like way. So I'm gonna explain more about this statement.
So when you say instances, you mean the
that's satisfied, yeah. Yeah, H for KNR's conjecture. So to explain this statement precisely, I have to introduce the notion of tree decomposition. I've just learned that it's more often to write the tree first and then the vertex subsets later. But I've been using it the other way around. But none of the referees pointed out so far. But okay, so yeah. But to make you comfortable, I'll try to stick to this order. Yeah. So this is here. T is a tree on F, and F is a family of subsets of the family of vertex subsets of H. And this is a tree decomposition. Probably almost all of you would know. If the following three conditions hold, for any vertex V, there exists some F. There is some X containing that V in F, and for any edge, there's some X covering that edge. And the third condition, which I often call Markov property, is that given any v in the intersection of two different vertex specs x and y, I have v in any z on the path from x to y. So if these are vertex specs and I've made a tree like this, and if I have some v over here and v over there, then my v must be all the way onto the path. So this is tree decomposition, and I'm gonna say that a graph H, given a graph J, a J decomposition, just to be short, a J decomposition is a special type of tree decomposition that decomposes H into pieces of J in a tree-like way. If this is a J decomposition, if it's a tree decomposition plus is a tree decomposition plus the following two conditions also hold. The first one is for every vertex spec X, the induced subgraph is isomorphic to J. So I'm really going to decompose my graph H into pieces so that are isomorphic to J. So each of these vertex specs induce a copy of J. And then the second one looks somewhat technical. For any edge, for any adjacent vertex specs X and Y in this tree, there exists an isomorphism. Well, there's an isomorphism because both graphs here, both induced graphs here are isomorphic to J, but there must be an isomorphism that fixes the intersection. So what I mean here is if X and Y intersect and induces the same copy of J, then I want this isomorphism is somewhat mirror-like. So there's this left-right sort of isomorphism between two pieces. This is a rather statistical condition that I need. So let me rephrase my theorem. So let J be complete L-partite or odd cycles. Then any J decomposable, which means the graph admits a J decomposition. A J decomposable graph H satisfies the K&RS conjecture.
So J is a set of graphs or a fixed graph?
J is just a fixed graph that's isomorphic to either complete L-partite.
So you choose one of
one fixed L or complete L-partite graph. It's more, I don't know how to glue different size cliques, say. That's harder. Right, so this is the statement. And the method, probably, I think, the method itself is more interesting than the result. Well, and the method uses some information theoretic approach. And here's a general lemma, so which implies this theorem. So suppose H is J decomposable. Then actually we can give an inequality for these homomorphism counts for H, which is, so the lower count for H is given by the number of J copies to the So given a J decomposition F, T, and F, there are, so each vertex back in F induces a copy of J, so there are this many copies of J, which can intersect to each other. And then I divide it by the multiple factors that I use, which are H, X intersection Y of G. Yeah. So this is general theorem. So this holds for any G. So this lemma, this inequality, is quite useful, and I'm gonna roughly state a slogan that, so what this lemma actually implies philosophically is when you can Cauchy Schwarz, when you can Cauchy Schwarz to count some graph, then you may expand in a tree-like way. In a tree-like way. To see what this means, let me give some examples of this inequality. So, for example, one standard application of Cauchy Schwarz inequality in counting graphs is this very basic inequality. But still, it's somewhat useful. This is almost as same as the Goodman's formula, and that means. So this means if I count the number of normalized count for the K12, which is just a star with 2 leaves, and then it's at least the number of edges squared. Normalized count for edges squared. And the proof of this fact is by Cauchy Schwarz inequality, and it's quite simple. Let me give a proof. So this is an expectation of x and y such that, say, x and y and z. So if I sample the random vertices on the vertex set of G, and then this is a probability that this is a graph homomorphism. So so this is an indicator function for G, which means my random vertex x and y are adjacent in G. Then this probability can be rephrased in terms of these indicator functions and its expectation. And then this is the expectation of some G of x squared, where G of x is the average of x, y given fixed x. So I'm just averaging over all choices of y. And then I have gx squared because the functions here are identical. So this is just a bunch of change of variables. And then if I apply the Cauchy Schwarz inequality, then I get the expectation of gx squared. This is by Cauchy Schwarz. And then if I plug this in here, then I get the gxy. So this is again x, and this for x and y, both x and y. That's squared, which is this squared. So this is a very basic, probably the most basic application of Cauchy Schwarz inequality. So what I do here is to, so when you find a copy of the star, then I just look at the neighbor of one vertex and then take a square size, take a square of the size of neighbor set, the normalized size of the neighbor set. That's what I do here. And then by Cauchy Schwarz, I can just average first and then square it, and that gives you the right count. So, and more generally, you can do this with star by using Jensen's inequality for convex functions. And what this lemma says is, if you could do so to count some graph H, then you could expand it in a tree-like way. So, for example, for another example, if I consider the H being a tree, then consider the so then it means that H is K2 decomposable by the usual obvious basic tree decomposition of the tree, which every vertex back contains a single edge. Right? So if I apply that inequality, then what I get is the T of G is at least the number of, so here J is K2, which is a single edge, and then the number of vertex backs is exactly the number of edges in my T, and then the factors in the denominator is just 1 because they're just single vertex. So this already implies Sorrentos conjecture for trees, which is not that obvious, though not new. And for another example, well, the next example would be the theorem over here. But to this end, we need some extra treatment. So let me sketch the proof of the theorem by using that lemma. So suppose H is J decomposable. Let me give a proof for just for the case when J is an odd cycle, which is notationally simpler. So proof of this theorem, say theorem 1 for this case. So if I apply that inequality, then I'll get some inequality like this.
So this lemma, in this lemma, J is assumed that
yeah, so we are taking J is an odd cycle.
In this lemma, so J is also restricted, or is
no. It's just for every J. For every J, yeah. So.
Is this lemma new or was it known?
As far as I know, this is a new one, but people really well. But the thing is, I'd like to find more applications, but many easy applications of this lemma are not really new results. So people quite kind of understood how to deal with this tree-like structure, problem by problem, but they didn't really observe that this kind of general inequality exists. That's what I think, and it's also used in it was implicitly used in my paper with David. Yeah, it implicitly appeared in my paper with David too, and yeah, we were just trying to phrase it in a better way. Yeah. So here's the inequality, and the major caveat when using this inequality is how to get rid of these factors in the denominator to get some meaningful results like this or the Sorrentos conjecture. For trees, we were happy because these were just one. But if it's not, then we need some extra treatments. So in this case, these intersections would be just a edge disjoint path because the induced subgraphs are just odd cycles. So if these two odd cycles intersect, then it must be the disjoint union of path. And the key lemma here is an inequality between paths, saying that so there are two lemmas. The first lemma is the even length. So the P2L means the path with 2L edges. I know it's slightly off standard, but I just want to stress that this has even length. Yeah, so that saying that the even length path dominates every subpath of it. Okay. By domination, I mean some sort of correlation inequality like this. Yeah. So this is first lemma. So that if there are a bunch of edge disjoint paths over here, then I can bound it from above, which would give a lower bound because the terms are on denominator. So this is the first bound that bounds here, and still I have to know what happens between the odd cycles versus the even path, and that's where the local density condition, which I didn't use much, comes in. So that means d, so 1 minus eta times d 2 times p2r of g. So this is general theorem, holds for any g, but this is for whenever g is rho d dense for suitably chosen rho. So that means we have some lower bound in terms of path of length 2r for the odd cycles. And what I do is, how much time? I've got some time. So, oh, and I must say that this is essentially by Christian Ryer on his paper of on the odd cycles on KNR's conjecture. And using these two lemmas, I can bound this because for the factors on here, I just plug this upper bound and times the, which is the number of edges in the intersection. So this is the number of edges induced on the intersection. Okay. Any question? Minus, sorry. So I'm giving the upper bound for each vector over here in terms of the even path of the, sorry, 2r. Yeah.
So the inequality, is it in the correct direction? So the lemma, the P
yes.
equal.
Yes, because we are going that way.
Yeah.
Yeah. So, and we are plugging in the upper bound of denominator to get the lower bound. Yes.
Right.
So every vector here is of form like this, or its product.
Yeah.
Yeah.
And
So we are plugging in this bound.
Oh, I see. So
Yeah.
the right hand side is yours, and then
Yeah. Yes. Sorry. Yeah. So we are plugging in this upper bound over here to obtain this one, and then we again plug the lower bound obtained by the lemma of Ryer. Then we have such a lower bound, and if you believe me, then this boils down to the right lower bound for a k-NRS conjecture. If you count the number of edges in the J decomposable graphs in terms of these vectors. Yeah. So this is the sketch of proof, and essentially the case for complete multipartite graphs are just the same. What we need is some lemma like these to cancel these vectors off by the vectors on the top. So this is application. And there are more applications, which I'm going to talk about briefly within 3 minutes. So there are more applications. So there's a term called common in remedy theory, which means whenever so a graph is common if we color Kn. If we color Kn, if we two-edge color Kn, then there exists at least 2 to the 1 minus number of edges in H. So H is common. H is common if given any two-edge coloring of Kn, there exist this many monochromatic copies of H. So to characterize these common graphs is an old question by, I think, Erdős conjecture that every clique is common, but it's disproved by Andrew Thomason in the 80s. And then there are some other results, but I don't have much time to mention them all. But there are an interesting result by Sorrentos saying that every triangle edge tree or triangle vertex tree is common. By triangle vertex tree, I mean I glue triangles in a tree-like way in such a way that the intersection is just a single vertex. So this is a special type of triangle decomposition in terms of these J decomposition language. So if the intersection of vertex backs are just one single vertex and every induced subgraph is just a triangle, then it's a triangle vertex tree. And similarly, triangle edge trees are trees like this. So it's triangle decomposition that every intersection has two vertices. So yeah, and there's a way to prove these results. Give a simpler proof of these results using this inequality or its hypergraph generalization. Yeah. So right. Yeah, I'm going to stop here.